For the second part of the extra Python lab, we're gonna use this example that we have already solved. So this is from lecture 11, and this is the example. It's a 1D heat transfer problem that we solved for the steady state. We had an essential boundary condition at the left end. We had a constant source term over the bar, and we had a flux boundary condition on the right end. And we are given the conductivity and the cross-sectional area. And what you did in homework 3, I want to say, is you did a mesh convergence study with a mesh of 2, 4, 8, and 16 linear elements. And we're just going to solve the same example with 16 elements, but for the transient. And then, so that one is, where do I have it? So that the part that I just uploaded, the other video, is I did the whole derivation, and then what we ended up with was this weak form, which looks very similar to the weak form for the steady state, with the difference that we need to compute this mass matrix. And this mass matrix is the integral of the product of the shape functions over the element, and this force vector in quotations. And that one is the integral of the shape function times the temperature integrated over each element. And I've uploaded some code already, which is the PL extra transient 1D heat, and I based it on the previous code that I have uploaded for the homework 3 solution. I just edited that. So you can see the beginning is the same, shape functions same as before. So linear element, shape functions and derivatives, Gauss points, so integration scheme. The definition of the problem is the same: length, source term, area, conductivity, flux. The mesh, I'm gonna use the 16 element mesh, and here I'm just creating the mesh. Now where things start to get different is here, as you can see from the, actually not that one, this one. From this term right here, what I need to integrate is the temperature at the previous time step. So I need an initial condition, I need an initial temperature field, and then I'm gonna keep on getting the next temperature field. So the initial condition is gonna be make all the nodes have 0 temperature, and then I'm gonna append that into this array where I'm gonna be storing all the solutions. So the initial one will be just zeros. Then I need to integrate over time. So I'm gonna get, instead of a single temperature field, for every time I'm gonna get a temperature field. Because what I'm gonna be doing is I'm gonna be solving this equation repeatedly. So I'm gonna start with some temperature field, and then I'm gonna find the solution for the next the temperature field at the next time step. Then this is gonna become the temperature field the previous time step. So this is gonna end up going into this term, and then I'm gonna solve for the next time step, and so on. So I need to have a loop over time. So as I say, the initial temperature is gonna be just zeros, and then I need to loop over time. So here I have 2000 time steps, 0.1 seconds. I need my stiffness matrix. This is the same as before. Mass matrix is different. It's also the same size as the stiffness matrix, but it's going to be filled out differently. This is the same as before. The source term, the flux term, same as before. This one is also different. This is basically the contribution from the previous time step. Then I can have my loop over elements. I need to assemble all of these guys right here. Same as before, read the x coordinates that make up this element, the length of the element. This is different. So now, because I need to use the information from the previous time step, I need to be able to read out the temperature at the nodes from the previous time step. So this t underscore 0 is the temperature at the previous time step. And I need this again because that will go into this force vector right here. And then so that when I finish solving these equations, I'm gonna get the temperature at the next time step. Then I need to replace again that this D will become the previous time step, so it will become T naught. So I need to read the temperature from the previous time step. Stiffness matrix, same as before. Force vector due to the source term, same as before. Mass matrix, now this is different. So the mass matrix of the element is also a 2 by 2, just like the stiffness matrix. But then I need to integrate, before I show you what I integrate. So the mass matrix, see, the stiffness matrix integrates the product of the derivatives of the shape functions. The mass matrix integrates the product of the shape functions without derivatives. So what I can have is I can use Gauss quadrature, 2-point Gauss quadrature, linear map, get from the xi, get the x, Jacobian for the linear map, shape functions at the x location, and then integrate the mass matrix. The mass matrix is just going to be Jacobian times weight times the function that I need to integrate. What I need to integrate is the product of the shape functions. So the outer product of n vec and vec will be, n1 n1, n1 n2, n2 n1, n2 n2, and then assemble into the global. So that takes care of the mass matrix. And then the other one that is different is this initial force vector. So again, if you go right here, what you can see is that I need to integrate shape function times the previous value of the temperature. So I can do that with Gauss quadrature. Again, initialize is a vector of 2 zeros, Gauss quadrature, Gauss 2 for example, for the given psi, get the corresponding x, get the Jacobian, get the vector of the basis functions, and get the temperature at that location. So Ti is the interpolation of the temperature inside of the element. So that will be N1 times T1e and N2 times T2e. And again, recall that T1e and T2e are basically the values of the temperature at the nodes from the previous time step. So I'm reading the previous time step temperatures, then I'm interpolating them, right? And then I'm integrating shape function times the temperature at the previous time step. Hopefully this makes sense. This is basically this guy right here. And then assemble. And that's it. Solving, same as before. Well, not same as before. Same idea as before. You can see that the system of equations is a little bit different. So instead of kd, I have 1 over delta tm plus k. Instead of just fq, fs, and fq and fs, I have fq, fs, and f naught. Actually, I am missing a 1 over delta t right here, because here I took the 1 over delta t out. So there's a 1 over delta t missing here. Sorry about that. So you can see that I'm gonna be using the matrix partitioning. The idea is the same as before. Flux term is the same as before. Essential boundary conditions, same as before. Partitioning of the stiffness matrix, same as before. But now I have the mass matrix, so I also need to partition the mass matrix. And then the force vector, before it was just minus fq plus fs. Well, now it's minus fq plus fs plus 1 over delta t f naught. And then solving, I need to solve, before it was just kf, now it's 1 over delta tm plus kf, right? And then the force vector, and here again, here I only had kef transpose, now I have 1 over delta t mef transpose kef transpose dE. And that's it. If I solve this, then I'm gonna get the node temperature. So that will be the temperature at the next time step. And I can save that. Now, before I go to the next time step, I need to basically switch. So this temperature, which is the temperature at the next time step, should become the temperature at the previous time step. So I need to reset for the time loop. So I make T0 node T. So that when I go back to the loop and go back to this step, what I'm gonna have in T0 is gonna be the the next time step. Does that make sense? So as you loop over this, T0 will be updated with the next time step temperature. So that's why I need this. After I solve, I need to reset for the next time step. And that's about it. You can plot it. I'm not sure this code is gonna work for everyone. I don't know if this works on NanoHub or Colab. I would have to check because this is a particular library to create videos. I just wanted to create an animation, and I'm gonna upload this code. So let's see if it works on your computer. But essentially, what you can get is the temperature profile over time. So you can get a video, and you can see, that initially everything starts at 0, and then it starts gradually going up. In addition to plotting this animation, I plotted for a few for like 10 time steps. I plotted the solution. So at time t equals 0, that I defined the initial condition to be everything 0. So that's this vector right here. And then what the code is doing, as I said, is getting the temperature at the next time step, and then at the next time step, and so on. And so after 2,000 steps, you can see how the temperature is evolving. And then what I'm plotting, this exact solution, that's the exact solution for the steady state. So you can see that gradually the temperature will go towards the steady state. So as time goes to infinity, then it will just stay right there. So it won't move. You can see that initially it changes very rapidly, and then as time goes on, then it approaches more and more the steady state solution, and then it will just stay there. So that's it. That's the transient heat transfer problem in 1D.